The building blocks of the solar system are quickly giving up their secrets. Two major missions are underway. The NASA OSIRIS-REx, which is now closing in on its target asteroid Bennu, and the JAXA mission Hayabusa2 to Ryugu, which is well into its observation leg of the mission, studying the asteroid up close. Both missions hope to return samples to Earth for a more complete study. A 3.5-year journey to asteroid Ryugu is over, and the Hayabusa2 science mission begins. Ryugu, part of the Apollo group, is potentially a threat to Earth in the years to come. It's an unusual asteroid, a CG type, meaning it has qualities of both C-type and G-type carbonaceous asteroids. It is just under 1 kilometer in diameter and fast-moving. As part of its payload, Hayabusa2 has several deployable landers, 2 Minerva IIs, the Franco-German mascot lander, and target acquisition markers for the touchdown.
Okay, we want to see the boulders. We have a chance to see the boulders in a vertical structure. We also see the crack in the boulders. There is also regolith. We know from the spectral information we have so far that there is something a little bit redder, something a little bit bluer on the surface. So that's very interesting because there are differences on the surface. We have the feeling that the bluer, it may be a little bit fresher than the redder. And that basically gives us a good idea of the history of the material on the surface. And of course, there are a number of landing sites which are red and blue, or which have red and blue in it, and that's probably preferred, at least for the camera, so we have a chance to see both of the surface units.
From the feedback I have obtained now from our principal investigators of the instruments seems to be that it's a very interesting asteroid, and that there are several aspects which is covering the science objective of each instrument.
First to be deployed to the asteroid were 2 Minerva probes. These rovers are based on the original Minerva craft flown on Hayabusa2, which unfortunately failed to land on their target asteroid. These ones, however, were successful. They have radioed back several stunning photographs from the surface of the asteroid, including this sequence of the Sun crossing the skyline as the asteroid tumbles.
Asteroid missions are very important and very interesting from the scientific point of view, because it is believed that asteroids and comets are bringing water to the Earth in the very early phase of the development of the Earth. And with this water and also organic materials, it is believed that life on Earth has developed. And very importantly is also there to understand the evolution of the solar system, because asteroids are supposed to be building blocks of our early solar system.
The Hayabusa2 mission has been years in the making. As with any deep space probe, years are spent on the drawing board developing the hardware and software. Then come years of construction and extensive testing. The aim of the Hayabusa2 mission is to learn more about the origin and evolution of the solar system. As asteroids account for some of the most primordial celestial bodies, Researching them gives us a glimpse into our cosmic past. Scientists are keen to learn more about the properties and structure of near-Earth asteroids in order to gain new insights into how our solar system formed and how water and life emerged on Earth. It's an audacious mission.
I mean, they're flying to an asteroid. Now we map the asteroid. Then a lander will be deployed like Mascot or Minerva. They're trying to do 3 samples, and then they have also explosive on board to produce a crater on the surface of in the asteroid. I mean, this is, to me, it's a unique mission they are doing, and we are part of it. So I'm really proud of it.
And of course, we are interested in the geology, the geomorphology, the structure, the size of the big boulders, and also the structure of the regolith, and giving some hints of the evolution of the surface, of the forming and evolution of the surface of Ryugu. Oh, I think for a camera, all of the rendering sites are quite okay. So the most interesting thing is to see the big boulders from the vertical structure. We really can look how deep they are in the surface. And there are many boulders on Ryugu, so I'm pretty sure we get a good view of this interesting part of this asteroid.
The second batch of asteroid landers developed by the German and French space organizations were launched and, after a short free-fall, successfully landed at the southern hemisphere of asteroid Ryugu. After bouncing several times on the rock-strewn surface, the 2 landers have begun their scientific research.
And you know that Mascot is made to bounce. That makes it robust, but it also means that the final resting location is not exactly possible to calculate it. So there's a dispersion of possible sites, and there is some variation in between. There could be, among these many possibilities, some bad ones. And we have to go to places where the chance to hit a good one is highest, but does not exclude that we end up in a bad one.
Autonomous handling doesn't mean that every Mascot is doing everything as he likes to. So there's lots of sequences and command stacks behind, which are carefully tested and planned. So the robustness of these sequences have to be tested against all these different conditions we can meet on the asteroid. So if we bounce or land more in the west or more in the east, for this, the input Mascot has, which he uses for his autonomously, this is really carefully planned and tested. And so there's all the work in, and I think we did a very well job, and so I'm relaxed.
With its 4 instruments, including the Micromica spectrometer developed by the IAS Space Astrophysics Institute at Orsay with CNES oversight, Mascot is set to analyze the mineral composition of grains in the asteroid's soil in an attempt to unlock its secrets at 2 sites just a few meters apart. They also took some fascinating images.
I think at least for me, the most important question is the big number of boulders. Where did they come from? Why has this asteroid so many boulders? Why are these boulders to some extent covered by the surface, so they are in the subsurface? And the question here is, what are the source of the boulders? Are they from the interior or coming from outside? Are they relict from some kind of collision from a bigger body, where Ryugu is now a relictic part of it? So I think that's the most important question.
Mascot was operational for over 17 hours, during which it collected data from the asteroid's surface and transmitted it back to Hayabusa2 overhead, which relayed the data back to Earth. The next probe to be released is the third Minerva robot, the largest of the Minervas.
I would like just to express again this amazing work which the whole team has done, DLR as well as CNES, as well as JAXA, surely. This was a very good example of a very good collaboration on an international level, and I hope that it will go on in the future.
GNC that has to tell the autonomy manager if we are on the right side or which side we should turn to uprighten.
For France, this was a big expectation.
The entire mission has been a close collaboration between nations. Japanese, German and French scientists and engineers have enjoyed over a decade of scientific cooperation, even if there are language barriers.
A realistic delivery with 6 slots in which the mascot...
I like it because it's a small mission with little overhead, and it's very nice to work with the Japanese because they are very success-oriented. They are willing to take risks. They have also, because of language issues, much less paperwork than NASA or ESA does. So most things are done in discussions, and you agree on something. You look into your eyes and say, yes, we do this, yes. And you rely on the words. You don't sign big papers. And that's something I like because it makes work so much easier and smoother and quicker.
Oh yes, the mission is very good. There are, in all the teams from Hayabusa mascot, there are very excellent engineers and also very excellent scientists. So I'm really confident and excited. That's the first time we do this.
The Hayabusa2 mission is very interesting from the point of view because Hayabusa2 is investigating a C-type asteroid. Ryugu is a very primitive asteroid which is supposed to have organic material on the surface. In addition, Hayabusa2 has got in situ science provided by the Mascot lander and also 2 to 3 further small Minerva landers, and it will bring some samples back to Earth so that we can investigate it then on Earth in the labs.
In the spirit of friendly competition, NASA was quick to congratulate JAXA for reaching their asteroid first.
This is Dante Loretta, leader of the NASA OSIRIS-REx asteroid sample return mission, congratulating you on the successful approach to asteroid Ryugu. We're all very proud of your amazing accomplishments so far, and we look forward to working with you together over the next year to maximize the scientific return from our 2 missions.
NASA's OSIRIS-REx probe is about to reach its target, Bennu, another CG-type asteroid close to Earth's orbit. A less ambitious mission, OSIRIS-REx will touch down and retrieve a surface sample, then return it to Earth.
Oh, asteroids are very interesting objects. So they are very primary. They are the fundamental things, the fundamental material of the solar system. And on the other hand, they have, to some extent, they cross the orbit of the Earth. They are dangerous. And just to know their structure, composition will help in order to avoid collision with the Earth if this may happen. And that will give us enough information in order to really find a way to mitigate this kind of catastrophic future.
And there is no shortage of conceivably dangerous asteroids out there.
It's one of the main points, of course, yeah, because we really cannot exclude it, but it's on a long time scale. But in any case, we know from the past, and we know from the past 4 billion years, that this is a real danger for planets.
"66 million years ago, one asteroid measuring 10 kilometers across completely changed Earth's climate, wiping out 2/3 of living species and consigning the dinosaurs to history books and museum displays. Fortunately, large asteroid strikes are very rare, but smaller ones can still be dangerous. Along with other organizations across the world, ESA is working hard to identify and track them.
We currently have a detection rate of something like 200 asteroids per month, and maybe 3, 4, 5 of them are objects which might hit the Earth. So currently we have 740 objects where we don't know if they will hit the Earth or not. There's none which is really a serious threat, which we currently know of. There's plenty of things out there which we have not yet detected, which we are still searching for, but from what we know right now, there's nothing which we have to really worry about. What we are worried is if a 20-meter object would approach. That was the case 5 years ago in Chelyabinsk, when a 20-meter object exploded over a city in Russia, and 1,500 people went to hospital because they were close to a window or they were hit by fragments, and they were not aware, nobody knew that this object would come. And this is what we could improve in the future, that our telescope would detect this a week maybe in advance.
ESA's new Fly-Eye telescope will conduct automated nightly sky surveys. It works by splitting the image into 16 smaller sub-images, greatly expanding the field of view.
We plan our Fly-Eye telescope in Sicily. We can scan the sky within 48 hours. So whenever an object bigger than 10-15 meters would approach, we should be able to see it beforehand, and then we would pass this information to the authorities.
Currently, the first Fly-Eye telescope is foreseen to be placed in Sicily, near the Monte Mufara. There are other 3 telescopes foreseen in the frame of the next project, and there are many advantages in having 4 identical telescopes, both placed in northern and southern hemisphere. The coverage of the both hemispheres is due to geometric reason, in order to cover the full celestial sphere. Then, considering that the telescope needs a clear sky for the observation, doubling the number of telescopes allows to compensate in case of bad weather conditions.
ESA's Fly-Eye telescope will improve our chances of detecting these potentially dangerous objects, while the asteroid missions will increase our knowledge of asteroids and look at ways of protecting our planet. The telescope was designed and built by a consortium of companies from Italy, Poland, and Romania.
The Fly-Eye telescope is based on a novel and original optical architecture that mimics, as the name says, the eye of the insects. In practice, it is composed by 16 independent and single telescopes that share a common primary mirror. This way we can join together different optical features that are difficult to combine together in a single telescope. And every single optical channel, every single telescope that composes the Fly-Eye telescope is provided with a focal plane which already provides a large field of view. The combination of the 16 field of views creates a very huge field of view. In practice, we have for each single telescope 2.75 square degrees of field of view that multiplied by 16 gives the 44th field of view of the overall instrument. This is very important due to the fact that with such a large field of view you can map large areas of the sky very quickly, and you can this way scan the full visible sky at least 3 times per night. A typical observation of the telescope is about 40-60 seconds exposure time. During this time, of course, the structure must be very stiff in order to avoid the vibration that could blur the image and diminish the possibility of the telescope to look for faint objects. And this is very important from the optical point of view, due to the fact that all the performances that are collected together in the telescope must be maintained also from a mechanical point of view.
Fly-eye telescope, due to its large field of view and also the capability to quick scan the sky, allow to arrive up to 3 complete scanning of the sky per night. This feature allows to implement what we call wide survey. What it exists today is what is called the deep survey, so a specific observation of an asteroid very far. But today we think we are the first, we are offering a service to cover all the world, because we can inform the population with a week in advance that an asteroid can hit to the Earth, so we can protect the population. This instrument can detect an object like a tennis ball at an orbit 1,000 kilometers, moving at 10 kilometers per second. After 10 detection, we can calculate the orbit with an accuracy of 20 meters along a track. So are important feature, and we can implement a really cooperative way between radar and optical.
ESA is currently working on a set of space safety and security activities, which focus on threats such as space weather, artificial debris, and asteroids. By enhancing the existing space situational awareness program, these will help us better understand the risks to our planet and prevent disaster.
Searching for asteroids and mitigating the risk of impacts, while at the same time collaborating with international partners. That's how I see how ESA can contribute to fulfill UN Sustainable Development Goals.
All going well, the Hayabusa2 sample will land in the Australian outback sometime in 2020. OSIRIS-REx will follow with a sample for return in 2023.